Dr. Jean-Daniel and AIMS-Cameroon for inviting me to give this presentation, giving me this opportunity to meet everyone. It's also nice to see how many people have come here for this talk today, because I see there's a lot of people in this meeting. So I hope that this is going to be an interesting talk and accessible for everyone. So the title you can see here is Fractional Calculus and Zeta Functions. My name is Aaron Fernandez from Department of Mathematics in the Eastern Mediterranean University in Northern Cyprus. So the title is in two parts, and this is because I'm going to talk about two different parts of mathematics and bring them together. So there is fractional calculus and there is zeta functions, and I'm going to give, as you can see up at the top here, I have the list, sort of the sections of the slides. So I'm going to give the background on both of these fields separately. I'm going to talk about what people have done in the past to bring them together, my work bringing them together, and then finally conclusions. So let me start with analytic number theory. So this is where zeta functions come from. This is the part of mathematics that brings together analysis with number theory. It's analytic number theory because some properties and ideas from number theory are applied using analytic functions. So this connection is useful because there are number theoretic things that can be described using analysis, and zeta functions are a particularly important example of this. So I'm going to define zeta functions on the next slide. Let me just say that often this field is studied from the viewpoint of number theory. For example, you have Dirichlet L functions, which are similar to zeta functions, but they're like zeta functions modulo a prime. And of course, when you take modulo a prime, that makes it more like number theory and less like analysis. But I'm an analyst. I want to look at this field, which is analysis and number theory together. I want to use the viewpoint of analysis. So here's the definition of the main functions we're going to be looking at. Riemann zeta function. This is one of the most famous, most fundamental parts of analytic number theory. It's defined as zeta of S. So S is a complex variable. It's traditionally called S instead of Z or something. You've got zeta of S, which is defined by this series, and the series converges provided that S has a real part bigger than 1. So that's quite a simple series. If S equals 1, it would be the harmonic series, which diverges. If S equals 2, it would be the sum of reciprocals of squares, and so on. You've probably seen at least some special cases of this series before. Then you can generalize this slightly to the Hurwitz zeta function, which is defined in this way. Instead of n, you have n plus x. So now there's two different variables. You have not only s, but also x, two complex variables. Lurch zeta function is another generalization where you have three complex variables. You have t and x and s. Now, all of these three functions are defined on the assumption that s has a real part bigger than 1. So that's an assumption for all of them, but we can get rid of this assumption using analytic continuation. So all of these definitions can be extended to all complex numbers s. So let me give some motivation and ask, why are these functions interesting? Well, the Riemann zeta function, this is, as I said, one of the most fundamental things in analytic number theory. It can be used to describe the distribution of prime numbers within the natural numbers. So that's a big question in number theory. How are the prime numbers distributed? How many prime numbers are there up to a given point? This is a big important question. And the Riemann zeta function is an analytic function which is somehow used to describe that. So there's a connection which is quite complicated between analysis and number theory here. But to give a simple connection, we can say the Euler product formula is a way of writing this function zeta s as a function of, or as an infinite instead of an infinite sum. And that's interesting because, of course, connection with prime numbers means a connection with number theory. So that's the Euler product formula. And the zeta function itself, it has this connection with number theory, but it's just an analytic function. It can be studied analytically. And from the analysis point of view, again, it's interesting because it turns out to be very hard to prove anything about this function, to prove any properties. So because this function is so difficult, many interesting mathematical techniques have been invented just from studying zeta functions. So the zeta function is useful in number theory, useful in analysis, and it's a key point of analytic number theory. Relationships between these three functions I've defined. If you go back to the definitions here, if you want to put x equals 1, then you have n plus 1, n starts from 0 there. That will give the Riemann zeta function. If you put t equals 0 in Lurch, then you go back to Hurwitz. The Riemann is a special case of Hurwitz, is a special case of Lurch. So when you go from Riemann to Hurwitz to Lurch, you are adding additional parameters. First you have only s, and then you add a new variable x, a new variable t, and by doing this we find some interesting results which do not have analogues for the original Riemann zeta function. But we also lose some useful properties. So by doing this generalization, you lose, for example, the Euler product formula. There is an Euler product formula for the Riemann zeta function, but not for the Hurwitz or Lurch zeta functions. So as always in mathematics, you generalize a little bit, you gain something, and you also lose something. Discussion of domains of these functions. The definition I gave originally for the series was only for S having real part bigger than 1. So we can say this is like the right half plane within the complex plane. And in this case, the Riemann zeta function is easy because you have this explicit series formula. You know that it converges absolutely, uniformly. You can prove lots of things directly from the series. Now, if real part of S is less than 0, then you have what's called the functional equation, which is a simple connection between zeta of S and zeta of 1 minus S. And this connection means that that left half plane of real part of S negative is also easy to analyze. Because if you want to analyze zeta S with S negative, then 1 minus S is bigger than 1, and so you can use the properties from this first domain. So what's difficult about the Riemann zeta function is when real part of S is between 0 and 1. So just in this finite strip of the complex plane, real part between 0 and 1, imaginary part can be anything. This is called the critical strip, and this is where all the challenges are. So in the next couple of slides, I want to just show a little bit of information about two things, two important open questions, open problems about the Riemann zeta function, and this will give you an idea of how difficult this field is. So firstly, let me mention the Riemann hypothesis. This is one of the most famous open problems in mathematics, and this is about the value of sigma, real part of S, if the zeta function is 0. So in other words, we're looking for zeros of the Riemann zeta function. And the Riemann hypothesis says that all non-trivial zeros of the Riemann zeta function, there are some trivial ones which are easy to deal with, all of them which are non-trivial should have real part 1/2. That's the Riemann hypothesis. Nobody knows if this is true or not. Most mathematicians think that it is true. So this is the critical line, sigma equals 1/2. And that's the line of symmetry. By the functional equation, you have symmetry between S and 1 minus S. Line of symmetry is where real part equals 1/2. So this question was first posed by Riemann in 1859. By 1900, it made David Hilbert's list of 23 most important open problems in mathematics. It was number 8 on the list. Very few of that list are still open problems. So most of them have been solved in one way or another, but this is one of the ones that's still open. 100 years later, in 2000, it made the Clay Foundation's list of 7 most important problems in mathematics. These are called the Millennium Problems. 7 for the year 2000, only one of them has been solved so far, the Poincaré conjecture. And for any one of those 7 problems, if you solve it, they offer you $1 million. So this is literally the $1 million problem. If you can prove that this statement is true or prove that it's not true, then you can get this $1 million from the Clay Foundation. This is just to show how big this problem is. It's been open for 150 years, since 1859, and in that time it's been very prominent. Many of the greatest mathematicians in history have worked on this, have studied this, but nobody has managed to solve it. So it's really difficult and really big open problem. Something slightly less big open problem is called the Lindelöf hypothesis. So this zeta function, but it's about the growth of the zeta function with the imaginary part. So consider this function on the critical line. So you put sigma equals 1/2 and you let t go to infinity. Then this is a function of t, and the Lindelöf hypothesis says that it grows more slowly than any positive power of t. So it's sort of bound on the growth behavior of this function. That's a weaker problem. So if you prove the Riemann hypothesis, then you know the Lindelöf hypothesis is also true, but not the other way around. So this is a weaker problem than Riemann, but it's still open. Nobody knows if this is true or not. And I'm going to show you just quickly some of the progress made towards this, again, to give you an idea of how difficult this topic is. So for a general sigma, real part sigma, let mu be the number such that zeta of sigma plus it, Riemann zeta function, as t goes to infinity, it's bounded by t to the power mu plus anything. So it could be t to the power mu times log t, or it could be just t to the power mu. It's this kind of behavior. So this is what sort of power function can you use to bound the Riemann zeta function? That's what we're looking at here on a particular vertical line in the complex plane. You fix the real part, you let the imaginary part vary, you say how does the function grow as you go to infinity. So as I said before, there is a critical strip which is difficult. So when sigma is greater than 1, you have the series formula, which makes the problem easy to solve. This mu is just 0. Then by the functional equation, for sigma less than 0, you can again solve the problem easily. You find that mu is 1/2 minus sigma. The function mu is also known to be continuous, convex, decreasing, non-negative. All of these are basic properties that just come from analysis of this type of function in general, the Dirichlet series. So from a trivial analysis, which was done by Lindelöf himself, you can show that mu of 1/2 is at most 0.25. So that's the trivial bound. Then there are some classical estimates from around 100 years ago. Hardy and Littlewood and Weil worked on this, and they showed that it is at most 1/6, which is 0.166. So that's quite a difficult proof. It's one whole chapter in one of the main textbooks on the Riemann zeta function is about these proofs. Then by the year 2000, you can see a Wikipedia page about the Lindelöf hypothesis. You can see how these numbers were improved over time. By the year 2000, the best known estimate for this mu of 1/2 was 139/858, which is 0.162. But the Lindelöf hypothesis says it should be 0. So just to recap how difficult this is, 100 years ago, they knew it's at most 0.166. 20 years ago, they knew it's at most 0.162. Almost no improvement at all, but that's 80 years of work. And for the Lindelöf hypothesis, you want to get this number all the way down to 0. And the Lindelöf hypothesis is only a weaker problem. It's not the big Riemann hypothesis. So this function, Riemann zeta function, is very difficult to understand, very difficult to analyze, very difficult to prove anything about it. And that's where all the challenges come from. So this was my introduction to zeta functions. Let me now do an introduction to fractional calculus. I'll talk about bringing the two fields together. So what is fractional calculus? This is the study of differentiation and integration to arbitrary non-integer orders. So if you learn classical calculus, you know how to take the first derivative, second derivative, third derivative, and so on. But how do we define the 1/2 derivative, or the minus πth derivative, or the 2 plus ith derivative, even going to the complex plane? How do we define these things? So this question, how do we define? There are many possible answers. There are different ways of defining fractional calculus. There are some different formulae which are equivalent to each other, And there are some completely different definitions coming from different motivations and different kind of circumstances. So fractional calculus is more complicated than classical calculus. If you want to take just the ordinary first derivative of a function, there's only one way to do that. If you want to take the 1/2 derivative, then you use fractional calculus, and there's many different definitions, even whole classes of definitions. So there is a very rich structure here. The idea of fractional calculus, just the idea of how do we define the 1/2 derivative, that goes back to Leibniz. So it's almost as old as calculus itself. 1695 people were already talking about this. But the idea was not developed really for a long time. And it's only in recent decades, in the last 50 years or even the last 20 years, that the research output in fractional calculus has increased massively. So people have got interested in it just relatively recently and started working in this field. Again, let me motivate this. Why should we study fractional calculus? From the mathematical point of view, okay, I'm a pure mathematician. So from my point of view, it's just a natural generalization. It's an interesting in using maths in the real world. Now let me give quickly the definitions. So the most common, I'm not going to go into lots of different definitions of fractional calculus. I will just mention the most common fundamental one, which is called the Riemann-Liouville definition. Riemann-Liouville fractional integral is defined like this. You have an integral formula. It's a convolution of the function f with a power function. You divide by a gamma function outside the integral. This works for any complex number alpha. See, alpha is the order of integration. It's now not only a whole number, it can be rational number, real number, or even complex number, but you need to have the real part positive so that this integral should converge. Then the Riemann-Liouville fractional derivative is defined to be an ordinary derivative of a fractional integral. So if you start with, let's say, the integral to order 1/2, and you differentiate that once, then you get the derivative to order 1/2. Or integral of order 2/3, you differentiate, you get the derivative to order 1/3. This is how fractional calculus works. The number c here, you can see there's a lot of notation. You've got d and I, which are derivative and integral. Then t is the variable, so you're doing with respect to t. Alpha is the order, and this c is a constant of integration. In fractional calculus, you need it for derivatives as well as integrals, so it's a constant of differentiation or integration. You can write derivative to order minus alpha equals integral to order alpha. This is like the fundamental theorem of calculus. You take a -1 order derivative, that should be an integral. So if we extend this in general, d to the order minus alpha is I to the order alpha, then this function is defined for all complex numbers alpha. So here we have real part positive, which becomes real part negative for the derivative. And here we have real part positive or 0. So when you put the two together, you get a definition that works for all complex numbers. This is an analytic function of alpha, and it's called a fractional differintegral. So you have this new word, differintegration, which is like differentiation and integration. They're now part of the same thing in fractional calculus. And that means that the Riemann-Liouville derivative is the analytic continuation of the Riemann-Liouville integral. So it's a natural way to extend. After you've started with this definition, then you naturally lead on to this definition for derivatives. Note that alpha, order, since it's now a complex variable, it makes sense to talk about an analytic function of the order, analytic continuation in the variable alpha. So that's a new thing, of course, in fractional calculus. Different values of c are useful. If you put c equals 0, then you get the very natural expected formula for the fractional derivative of a power function. This would not work if c took a different value. You need c equals 0 for this. If you put c equals minus infinity, then you get a natural expected formula for the fractional derivative of an exponential function. So let's keep the general c. We don't set it to be only 0, to be able to capture all of these different behaviors. We want to be able to say, we can get this nice thing for power functions, but also we can get this nice thing for exponential functions. So we keep the general C. More justifications for Riemann-Hubel fractional calculus come from Fourier transforms, Laplace transforms. They work in a nice expected way. The product rule generalizes to a fractional Leibniz rule, again in exactly the way you would expect. Like if you write down what happens for repeated derivatives and then what you think would happen for fractional derivatives, that is exactly what does happen. So it's kind of natural, this Riemann-Hubel definition. One thing which does not work as expected is composition. So in classical calculus, if you take, let's say, the second derivative of the third derivative, then you should get the fifth derivative. Like the numbers go together like powers. In fractional calculus, this works for integrals. Integrals have this semi-group property. If you take a fractional integral of a fractional integral, you get another fractional integral, but not for derivatives. So if you take the 1/2 derivative of the 1/2 derivative of a function, you do not necessarily reach the first derivative. So that's an unexpected thing about fractional calculus. It's one of the properties that you lose by generalizing. Of course, as always, when you generalize, you gain some properties and you lose some properties. So now I've introduced both zeta functions and fractional calculus. So zeta functions are the subject of some of the hardest and most famous open problems in maths. Analytic number theory, throughout its 150-year history, it's attracted some of the greatest minds in mathematics, both from number theory and from analysis sides. Fractional calculus, on the other hand, it's an old idea. It's more than 300 years old as an idea, but it's been mostly ignored until the last 50 years when it's grown massively and discovered applications in many fields of science. So as a mathematician, as an analyst, we can look at both of these, zeta function and fractional calculus. We can say these are two important parts of analysis. So why are they never united? Why has nobody studied zeta functions from the fractional point of view or applied zeta functions in fractional calculus? Why not bring these two fields together? So of course I say never, and it's not quite never, because they have been united sometimes, but very rarely, much more rarely than you would expect. So that's what I'm going to cover in this talk. I can give you an overview of all the times that these two have been brought together, all the people who have worked on uniting these two topics. Let me start with Jerry Bruce Kuiper. So he died in 1995, so he's not with us anymore. But at the age of only 41, he was killed in a bicycle accident, January the 18th, 1995. This image I've shown on this slide is from his obituary in the Mathematica journal. He had an obituary written by Stephen Wolfram because he was working, as you can see here, he was working in Wolfram research on numerical estimates of special functions. So if you're ever using Mathematica, if you're doing calculations on a computer of special functions using Mathematica program, it's likely that somewhere you're using some code which he wrote. So he was an important part in the development of Mathematica. I'm not going to read through all this, but I'll just point out the interesting things, which is that he was interested specifically in zeta functions, specifically in the Riemann zeta function and the Riemann hypothesis. And he wanted to find formulations of the Riemann hypothesis that would make it easier to investigate numerically. And when he died, they found lots of his programs which were running, doing something with zeta functions, but nobody exactly knows what, because he could have interpreted the results if he hadn't died. A few months before he died, Kuiper told me he felt he had made considerable progress, it says there. But what I want to focus on is his master's thesis, which is also mentioned here, his master's degree in 1975, where he showed that the Riemann zeta function could be expressed as a fractional derivative of the gamma function. So this was the first time that you see zeta functions and fractional calculus brought together. here we have Riemann zeta and fractional in the same sentence. And this man, Kuiper, in 1975, he was the first person to make this connection. So this was his master's thesis, Ohio State University, 1975, fractional calculus and its relationship to Riemann zeta function. Now, you would think this is an important result. This connection, a new connection, was made for the first time between two different fields of mathematics, and zeta functions are very popular among top-level mathematicians working on very hard problems. Fractional calculus is very popular nowadays in the years since then, so it should have taken lots of citations, lots of interest. But if you look it up on the internet, if you look up this thesis on, for example, Google Scholar to see how many people have cited it, you will see that it has just 5 citations. And if you look at who has cited it, it's only me. See here, A. Fernandez, A. Fernandez, A. Fernandez, all of these results. So I am basically the only person who has appreciated Kuiper's work enough to continue in that direction, to build on his work and to do new things connecting fractional calculus and zeta functions. I feel like every time I give this talk, I'm multiplying the number of people who are even aware of this Kuiper master's thesis. So I'm going to summarize Kuiper's methodology. Let's see some actual mathematics in this talk. I'm going to show you what he did, how he did it, and the result he reached in the end, just briefly. We start from the Hurwitz zeta function. Remember, that's Riemann zeta function with 2 variables. You have the s and the x. Apply a differential with respect to x. So you have this function, it's written as a series. You apply d with respect to x to the order alpha. And that's the fractional derivative of essentially a power function. It's x plus constant to the power of something. So you get some extra gamma functions in there, and make some assumptions on the variables just to make sure that things converge. Alpha should be bigger than 0, s bigger than 1 in real part. I'm putting in an extra zeta of s here, because if you take the derivative of a constant, it's 0. We're doing with respect to x, so we can put in a function of s there. It's just going to make things neater later. Zeta s minus zeta of xs, and then you get the same thing here. And this series, the gamma functions can be taken outside, they don't depend on n, and this series becomes again another Hurwitz zeta function. Now I want to let s tend to 1. So we use a result about zeta functions. As s tends to 1, this Riemann zeta minus Hurwitz zeta tends to the digamma function plus the Euler-Mascheroni constant. This is just a known fact. So in this expression, the part in square brackets, that goes to this digamma plus gamma. And the part on the right-hand side, where you have gamma of s plus alpha over gamma of s, that becomes gamma of 1 plus alpha, and you have zeta of x 1 plus alpha. So it looks like this. So that's an identity. On the right-hand side, it's basically the Hurwitz zeta function. You have Hurwitz zeta function of x 1 plus alpha with some other things. These are easy, just gamma function and power function. And on the left-hand side, you have the digamma function, this psi, which is gamma prime over gamma. And this gamma is a constant, so again, it can be ignored inside the derivative. So this is the end result. And if you write s equals 1 plus alpha, then you get a result for zeta xs written as a fractional derivative. What we've shown here is the Hurwitz zeta function is a fractional derivative of the digamma function. The variable s, the second variable there, appears as the order of differentiation. And also we require real part of s to be bigger than 1, because s is 1 plus alpha, real part of alpha is bigger than 0. So we needed to use real part of s bigger than 1, but we get this nice result for the Hurwitz zeta function as a s minus 1 fractional derivative of the psi function. For the specific case of Riemann zeta, you put x equals 1. You put x equals 1 here, then you get this identity, which is again true for real part of s bigger than 1. For interest, I show a screenshot of this theorem taken from Kuiper's thesis, the 1975 thesis. I think you can find the full text online, or maybe I found it in a library. Anyway, this is how it looked. And I was interested to see that back then, of course, they didn't have LaTeX, they didn't have maths formatting software. So this was written on a typewriter, and the Greek letters were written in by hand. You can see things like psi and infinity and zeta as his handwriting in his master's thesis. So just for young people like me who have always been able to use LaTeX, it's interesting to see that it used to be like that. Kuiper's work is largely unrecognized. As I showed before, nobody has cited this except me. But two other groups of researchers have worked in some way on connections between fractional calculus and zeta functions. So I'll summarize this quickly. We have the Italian group, Emanuele Guariglia and a couple of others working with Carlo Catani in some of these papers. They have been working on fractional derivatives of the Riemann zeta function. They didn't use Riemann, they used a different model of fractional calculus. But the comment I would make here is that Kuiper wrote the Riemann zeta function as a fractional derivative. So the connection sort of emerges naturally. Whereas these guys, they started with the Riemann zeta function and they applied fractional calculus to it. So it is bringing the fields together. It's an interesting thing to do, but it's not discovering a connection. It's more like creating a connection. Then we have Harry Srivastava and some others, Schreider, Lin, and a couple of other co-authors, have been working on fractional calculus relationships between modified Hurwitz-Lurch zeta functions with several extra parameters. So here we have fractional calculus relationships, but you need those extra parameters to find the relationship. So it's like, instead of Riemann is just one variable, Hurwitz is 2, Lurch is 3. If you've got 5 or 6 variables, then you can get new connections. So it's like the 6-parameter zeta function is a fractional derivative of the 5-parameter zeta function, which again is interesting. It's a connection, but it does not give any interesting information. If you get rid of those extra parameters, then you have nothing. So these are the other groups that have worked on connections, fractional calculus and zeta together. Now I want to go on to my work combining these two fields. So we have my recent paper, well, not so recent anymore, the Lurch zeta function as a fractional derivative. So I wrote this in 2017. It was accepted for publication in 2018, finally published in 2019. This journal is not free, but you can find the preprint on the archive. I've given the archive link as well, if you want to look at this. In this paper, inspired by Kuiper's work, I discovered a new way of writing zeta functions as fractional derivatives. This time, the starting point is the Lurch zeta function, not Riemann or Hurwitz, but Lurch with 3. The third one is vital in the proof. So we need to start from Lurch, but you still get an interesting result for Riemann when you set t equals 0, x equals 1, whatever you need to do to get back to the Riemann zeta function. So let me show you how this proof works. Remember the definition of the Lurch zeta function. It's a series, it's written like this. And my idea was to see this somehow as a fractional differintegral. So you have an exponential function there. If you take a fractional derivative of an exponential function, then you get a power of the exponent. But we don't have a power of n here, we have a power of n plus x. So I'm going to multiply and divide by a couple of things. 2 pi I to the power of s and minus s, e to the power minus 2 pi I t x, e to the power plus 2 pi I t x. So this is just the same thing with putting a couple of extra terms in, taking them away again. The reason for this is that what's inside the sum now is exactly the fractional derivative of this exponential function with respect to t. So you take everything in the exponent that's not t and raise that to the power minus s, which is exactly what you have there. So now you have a series of fractional derivatives. And you can swap this to write a fractional derivative of a series. I'm skipping some steps here in the logic, in the mathematical rigor, because of course you would need to prove that this series converges, that you can actually swap the summation and the differentiation, but I'm not going into all these boring details. I'm just showing you the key idea. So now we have a fractional derivative of a series. This series is just a geometric series. You have something to the power n summed over n. So you can write this as 1 over 1 minus that thing, and then you get Lurch zeta function equals power function, exponential function, elementary things, fractional derivative of this thing inside the brackets is again an elementary function. You only have exponential functions and a little bit of division. So actually where the most difficult part of this proof is in extending the domain of validity. So this proof used above, used the series formula, used some other assumptions, and in the end, these are the requirements on the three variables. Now, with some tricky arguments, some analytic continuation, some functional equations, we can relax these assumptions. So the assumption on S is not needed at all. The assumption on T is still the same, and the assumption on X becomes this. So you need the imaginary part of X to be positive or 0, and X should not be a negative real number. So this is the theorem. Lurch zeta function equals power exponential fractional derivative equation of exponential functions. Now that's interesting because it means that, as I told you before, the Riemann zeta function is a very difficult function, a very complicated function to analyze. But all of that difficulty is somehow encoded in a fractional derivative. You look at what's inside the brackets there, that's easy. That's just an exponential thing. So that's easy to analyze, but when you put it together with a fractional derivative, then you get all the complexity and difficulty of the zeta function. Let me just mention the result for the Riemann zeta function. Riemann zeta, of course, is a special case of Lurch zeta. So when you make a substitution for x and a substitution for t, then you get a result for just zeta of s. Zeta of s looks like this, or alternatively like this, depending on which assumption on s you want to use. So even though I started with extra parameters, I started with a Lurch zeta function, we still get a result for Riemann zeta. Continuing the above results, I have another paper together with Jean-Daniel Gida from AIMS-Cameroon. We wrote fractional differential relations for the Lurch zeta function. This is not published yet, it's still under review, but the preprint again is available on arXiv. In this paper, we started from theorem 1, Lurch zeta function as a fractional derivative, and we applied various derivatives in order to obtain new results and relations for the Lurch zeta function. This is our starting point, Lurch zeta function as a fractional t derivative. With respect to t, order is minus s. What can we say about the t derivatives of this function? We're going to take a fractional t derivative, and we need to use here a fractional Leibniz rule, because we have a product of two things. We have this is a function of t, that part's not a function of t, so just take it outside, but this is a function of t, times this fractional derivative, which also depends on t. So we have a fractional Leibniz rule, which is binomial coefficient, n order derivative, and alpha minus n order derivative. Now we also assume that real part of s is positive, so this fractional derivative is actually a fractional integral. D minus s is is, so it's integral to order s. Fractional integral has a semi-group property, so when you take d, you just add together the two orders, minus s plus alpha minus n. Meanwhile, differentiating an exponential function is easy. You just multiply by the exponent to the power n. Now this thing here, if we mess around a little bit with powers of 2 pi I, then we can get exactly the right power of 2 pi I there. You've got to the power s, to the power n, and I put minus alpha and plus alpha outside. So you have fractional derivative to the order minus s plus alpha minus n, 2 pi I to the power of the same thing, this exponential term, and what you get there inside the sum is again a Lurch zeta function. It's this same formula with s replaced by s minus alpha plus n. So what we get is the t derivative of the Lurch zeta function is a series of Lurch zeta functions. So that's an interesting result. If you use just an ordinary derivative, so if alpha is a natural number, then this will become a finite sum. But if it's fractional, then you have an infinite sum and infinite series of Lurch zeta functions. This is partial t derivatives. Now let's look at partial x derivatives. Starting point is the same, Lurch zeta function as a fractional derivative, and we want to apply d by dx to this function. Again, we have to use a product rule because you have a product of one function of x and another function of x there. So we use the product rule, differentiate this one with respect to x minus 2i by t, and then differentiate this one with respect to x, which is going to be 2 pi I t. Notice that that's a t derivative, this is an x derivative, so we can swap them. If you take x derivative of t derivative or t derivative of x derivative, same thing. So then we have the fractional t derivative of 2 pi I is constant, t times this exponential thing in terms of t. So then we use a special case of the fractional Leibniz rule, which looks like this. Substituting that in there, we have t times the derivative of this exponential thing minus s times the derivative of, again, this exponential term. First term there cancels with the second term. You've got minus 2i by t plus 2 pi I t. After this cancellation, we're left with just minus s, 2 pi I to the power of s plus 1, this exponential term, and the fractional derivative to the order minus s minus 1. So what this is, of course, is the Lurch zeta function with s replaced by s plus 1. See, it's that formula there, but instead of s, you write s plus 1. So we get L of txs is minus s times L of txs plus 1. That's for first order derivatives. Then by induction, you can generalize this to kth order derivatives. Take the derivative to order k with respect to x, then you get again a Lurch zeta function with a multiplier. So this is our theorem 3. Partial x derivatives of Lurch zeta function, another nice functional relation. This can also be extended to fractional x derivatives. Instead of k, you can put alpha, you can take a fractional derivative, and you get again the expected result. But the proof of that is too long, many ideas involved, and it would not fit on these slides, so I'm leaving it out. Let me conclude then by comparing all the different results, the different people who have worked on fractional and zeta together. We have the Hermite zeta function as a fractional derivative of the digamma function. The complexity of zeta is encoded by fractional calculus. Zeta function is very complex, very difficult thing, but all of that difficulty is given by the digamma function with a fractional derivative. You put those two things together and you get all this complexity. The problem with Kuiper's formula is that it's only valid when s has real part bigger than 1, and that's the easy region for the zeta function. So it's not that useful, because where we really want to know about zeta is when the real part is between 0 and 1. Still, it was important progress. He was like the pioneer of this connection. Then more recently, we have Guariglia, who studied fractional derivatives of the zeta function. Interesting study, but no new expression for zeta itself. So he didn't write zeta as a fractional derivative. Srivastava, fractional link between multi-parameter zeta functions. So again, interesting study, but it tells us nothing about the original zeta function. You need those extra parameters to get any result. And my work expressing the Lurch zeta function as a fractional integral of an elementary function. Elementary meaning it's only exponential functions, a little bit of division, and this means all the complexity of zeta is encoded by fractional calculus. You have an elementary function and a fractional integral, you get all of this coming out, and this formula is valid for all complex numbers S. Not only the easy region, but any possible number S in the complex plane. So this is my conclusions. Zeta function as a fractional elementary function, all that complexity, this kind of differential equation. You don't solve for the function, you don't solve for the variable inside the brackets, you solve for the order. You want to find which values of x leaves this to be true. That's something you can only do with fractional calculus, of course, because now the order becomes a continuous variable. Hopefully, fractional calculus can be used to attack zeta functions. Hopefully, a better understanding fractional calculus, for example, equations like this, like Riemann and Lefebvre. Here's my list of references. A few standard textbooks at the beginning: fractional, fractional zeta, Kuiper's thesis, 3 papers of Guerrilla, 3 papers of Srivastava, and then my 2 papers at the end. So that's the end of my talk, and thank you everyone for your attention.